Okay, good morning, everyone. So we've done a lot of really good exploring applications this week when it comes to the ABI. And the ABI is this known quantity, this increasingly known quantity. The GLM is kind of the odd bird in the room, not because it's any less capable, but because it's sort of this mystery to us in the operational world. We don't. We heard all these great things about it during the training, and then silence. We've been kind of on radio silence since. And you'll see over the span of this case study sort of why that's the case. It's not a problem necessarily with the instrument. It's a lot of unknowns that we have getting the data into AWIPS. But it's still tremendously capable. So we have a case from Huntsville that we haven't had any interesting convective events recently. So we looked west to Norman and the central Oklahoma area to find a decent case. So we'll look at October 21st of this year, so just a couple of weeks ago. There was an enhanced risk out for central Oklahoma, and you had storms that were discrete off to the west, fired along the dry line, and sort of congealed into a line with embedded supercells as they moved into the I-35 corridor. So what we're going to do, we're going to focus, since this is the first time many of us have had the chance to look at GLM data in any form, we're going to look at sort of the most basic events, basic applications of GLM, which is severe weather, looking for a lightning jump, for severe weather forecasting, and then the second part we'll talk about public safety and impact-based decision support. So the first one we're going to look at was a little bit east towards the Shawnee and Seminole areas. Off the screen to your left, to the west, is this congealed line with sort of embedded supercells in it. And you can see it here. So you've got sort of this broken line. There are glowing segments. There are some areas where there are kinks in the line suggestive of embedded supercells, but if you aren't necessarily, I'm not even going to say anything about Norman's operations. I'm just looking at it from the lightning perspective. So if you were just looking at the radar, you might not necessarily see anything that draws your attention. So we're going to focus on this area between Trivia and Seminole here. So at 2229, what you have on the bottom left here is GLM events. So these are the most basic pieces of a flash. These are the pixels that are lighting up, and these are the pixel level changes in brightness that are occurring. On the bottom right are the groups. So this is the second level of GLM data. So the events that are getting grouped together. And so one thing you'll see here, and one reason that the data haven't necessarily been made available in AWIPS, you start seeing some artificial boundaries because so we've heard 8 kilometers thrown around a lot with GLM. Oh, well, 8 kilometers is going to be 8 kilometer data. Well, it turns out that those get larger as you get farther out from data. So you're starting to have problems mapping 8 kilometer pixels to what are no longer 8 kilometer pixels. This is something they've been working on, it's been something they've been fixing, and in the final implementation of what gets into AWIPS, this has been resolved, but it's an example of why this isn't out in operations yet. This is something that they discovered and it had to be resolved first. So that's what's happening in the lower left-hand panel. The lower right-hand panel, those groups, that's not subject to the same limitations. And before I go any further, I should say the events and the groups don't represent what will be coming into AWIPS. It's what we have right now with what the OPG and what some of the collaborating centers like the NASA Support Program have. But what will be coming out into operations is sort of a blend of the events, the event density, and the flashes. It's going to be the flash extent density, so you'll get a true picture of the extent of a flash, but you won't necessarily, you won't have the some of the issues that you get when you start looking at individual pieces. So here we are, going back to the 229 UTC. This is an interesting line, not necessarily anything that would draw your attention. Certainly kind of a surge to the northwest of Tribby that maybe would draw my attention from a warning perspective. Let's go forward, scan. And you start to see things starting to light up on lightning. The event density has increased a little bit. Certainly, the group density has increased a little bit. Another limitation that has been a factor to this point, another thing that they have resolved in some of the development, is that there is a parallax effect. So the pixel we're watching is far down here, sort of southwest of Seminole, but that actually corresponds to something farther to the northwest on the radar. So there is a parallax effect here. Again, something that's been troubleshot, worked through, and will be corrected with the operational implementation.
And this is 1 minute.
And this is 1 minute, thank you, Chad. This is 1 minute data, so this is updating every minute.
So 36 to 74 change in 1 minute, basically.
Yeah, so thank you, Chad. So you had a significant uptick in the number of groups detected with this updraft in just 1 minute. Let's go forward one more, and you have another uptick to 61. And you have a similar uptick in the actual portion of the line. There's an uptick to the northwest too. So you have sort of concurrently increasing updrafts. We're looking for increase in total lightning because the volume and the strength of the updraft have a nonlinear relationship to the amount of lightning that gets produced. So as your volume and your updraft strength increase, you have this dramatic increase in lightning. So where we see a lightning jump, that's indicative of potential for severe weather. So we step forward again to 233Z, and there's a dramatic jump. So we went from, I believe it was 61, we went 36 to 74 to 61, and then all the way up to 120 here at 233. And again, we're looking over those scans. You may be seeing a little bit of an enhancement in the going segment, and almost immediately after this happens, you start to see the bow turn into more of a mesocyclone, and it becomes significantly enhanced here near Brooksville and West Fargo, and it actually. The tornado that occurred, this was Seminole tornado. The tornado that occurred actually occurred when the outflow boundary interacted with this mesocyclone, but there was a pretty good signal with the GLM groups as we led up to this. So as you saw, we went from, it was about 34, I believe, at the start, over to 36, I'm sorry. So over the span of 4 minutes, you went from 34 groups all the way up to 120 groups. And then moments later, you have this corresponding mesocyclone intensification. And there's some research suggesting that this is a common occurrence, that you have the updraft strength increasing and corresponding increase in mesocyclone intensity. So this is kind of our first case, and like I said, the actual tornado occurred about 15 minutes later as that mesocyclone interacted with this outflow vector. So there was actually a pretty good amount of lead time leading up to this tornado.
So we have 4 examples. Why don't we take Q&A quick between each one? How's that? Okay. So we don't have to go back and forth between times. Is that all right?
All right, questions? Let's take a quick reminder, Slido for folks that are joining remotely. Questions, comments from the audience here first.
So, the parallax is making it hard for me to tell. In the northwest part of that event, there's a lot there that I assume is related to the fairly robust looking convective. So
yes.
So what Chad is circling now, where is the lightning for that? Is that just to the east or mapping it?
Yeah, so the convective, the kind of Boeing segment there is this cluster of high events and groups that Chad is now circling. So that it's not a huge parallax issue, but it's enough, particularly in this kind of a case where it's a QLCS, it's enough to be a little bit distracting with regards to, okay, which updraft am I tracking?
It's important to remember that, and please, Scott, Steve, Brian, correct me, that it's supposed to, the lightning, the GLM is supposed to be like Earth located, geolocated, right? So the parallax is an artifact of maybe early data that is going through, development. There shouldn't be much parallax, like satellite imagery where you'd have parallax. Is that correct?
It's not Earth located. It's located at a certain height of this chart.
Okay. So it's a different type of issue than like overshooting top parallax, where you always know it's displaced, poleward and then to the left or right, depending on where you are in relation to the satellite.
That's what I was going to say, Chad. The traditional parallax, like we saw with other in the ABI, is actually almost the opposite of this, because parallax shouldn't be putting the GLM to the, what is it actually doing now? I know it's to the east and maybe a little bit to the south, and it actually should be to the north and west.
Right, it should be very close to the storm.
So, and this is one of the handful of significant issues that's being worked on the GLM, and that is with the geolocation of the data. And I'm not clear, and maybe Scott or Steve knows this better, is what we're seeing here, is it an artifact of the attempt at parallax correction in the GLM, or is there some other mapping error, or is it a combination of both?
Yes, so I can chime in on that. For those who haven't met me before, I'm Scott Orlowski. You may have seen my name places, focus on the GLM, but I wanted to make the point here that this early on, we may label it as parallax, but it's a combination between parallax and image navigation. And so the ground system is still working on how best to navigate the image. And so those are things that are improving in time and should be much better later this month. But yeah, the parallax issue, we'll still have to consider what the best way to do. There was a requirement to correct it, just kind of as the program was developed. And so as we first get this data out into the field, that will be one of the big questions. Is that something that should be done, or is there a different way that we should locate this data within the AWIPS environment?
Scott, since you have the mic right now, please address the Slido question, because I'm not surprised it's the first one asked. Everything that I've read would suggest that you should proceed with caution when comparing satellite sensed lightning versus Earth networks. just comment on doing that, I guess.
Yes, that's an important distinction to make. The way they detect lightning are totally different. So the ground-based networks detect the radio waves that are emitted by lightning, whereas the GLM sees the optical emissions. And so the processes are different, and what the networks are observing are different. You should have similar trends, though, where the Earth networks has a lot of sensors, where they have very good detection efficiency. I imagine you'll see very similar trends in the flash rate. If you go out west where they have fewer sensors, you're going to see differences between what the Earth networks is reporting and what the GLM is reporting. One of the main things, and I think later in the talk here, Brian will address this, is earlier you saw the NLDN and the ENTL up there, and it was real salt and pepper. There was a lot of variability, and what that shows is that certain parts of the lightning flash emit the radio waves more efficiently, and so you don't have this continuous of a field. Now the GLM will see the continuous field. It's the light that's emitted out the top of the cloud. And so that's one of the big differences that you'll see is where you had more kind of sporadic lightning even when it's more intense. And now with the GLM, you'll see the whole footprint of those flashes. And so the data sets will be complementary, but they also should be used a little bit differently.
One last point on navigation. Lockheed is to process data for us. And the navigation for the GLM is with half a pixel. But the errors in implementation of the Lockheed code in the ground system has been one of the problems. So that's what it's being fixed. So it should get there. Correct me if I'm wrong, I think November 30th was the targeted date for that implementation.
Yep, that's right. And real quick, Brian, before we comment on, talk about the lightning jump. I know this is an event outside of the can you comment quickly on, in your own office, how often or how frequently during operations are your folks taking that into consideration?
Right, so from my perspective, there's been we've had access to a North Alabama lightning mapping array, which operates the same way that Scott just mentioned, in that it's detecting the radio waves emitted by lightning. So again, different technology, but we've had access to the North Alabama LMA for almost 15 years now. So we have more cases than I could count where there's been a very clear lightning jump that's occurred before any type of severe weather, not just tornado, but hail and wind. And the total lightning jump doesn't necessarily predict what kind of severe weather you'll get. That's where the forecaster comes in. We still have to know the environment. We still have to understand what the trend is and what's happening with the radar to get out the right kind of warning. But the total lightning is an indicator that something is happening, and something is happening. Your updraft is strengthening, and that's an indication that what severe weather you're anticipating is about to occur.
I think we should take
both of those. Okay. So the second is, so it's probably Scott or Steve. The last question up there, which was okay first. Would it be preferable to simply not parallax correct the GLM, so it would be better aligned with the AWIPS?
That's one of the main things we're going to be looking at with the initial implementation. It is to see, is this throwing things off? I know when you start looking at different data sets and how the offsets are different, it can really get confusing. And so that'll be one of the main questions that we ask forecasters when we first get the flash extent density into operation. Should we keep doing what we're doing, or is there a better way?
And if I could interrupt, I mean, I think this is exactly why. I mean, this is brand new. You know, this just to reiterate the fact that they've had instruments like this on low Earth orbiting satellites, but this is essentially brand new technology. So there are a lot of things that we have yet to discover, not just in terms of operating the instrument, but in terms of the operational impacts and how it, I mean, no forecaster, at no point during this presentation am I going to use the lightning by itself alone. The lightning is almost always used in concert with some sort of other piece of data for decision making. So it's going to have, we're going to have to figure out these kinds of things where, okay, is it better to view it in the context of ABI? Is it better to view it in the context of the radar? How do all of these things work together?
Either case one is a nighttime tornado, case of high noon in summer, how much would the detection decrease? So instead of 178 events, for example, how much would it?
Yeah, it's a great question, and one of the distinctions that needs to be made for the GLM. One of the big advantages of the GLM over the ground-based networks is at any given point in time, you have relatively uniform coverage throughout the field of view. Now, you do have a difference from day to night. The specs are the GLM should see 90% of flashes at nighttime and 70% of flashes during the day.
Yeah, the spec is 70% total lightning detection over a 24-hour period. So you could have lower performance and still need spec. The most information we have right now is we flew a post-launch brilliant beam with an optical instrument in ASCR2. We had 10,000 flashes, and the result of that was daytime detection of 79% and nighttime detection of 88%. It's a limited sample, but it exceeds would exceed the spec that will hold true. So in regards to daytime, the drops, but right now it supersedes the basic 70% spec. So that's good news.
Okay.
All right, and I would be remiss on the line, sort of imagine sort of hovering over the auditorium. On the line, we have Jeffrey Stano, who's the GLM liaison, calling in from Huntsville. So we have a third lightning expert here that's part of the conversation. So the second severe weather case, as I mentioned, so we've got one severe weather case now. The second severe weather case we're going to look at is actually the Norman tornado. How many here, did anyone see the video of the tornado hitting the power lines right in front of the car from this event? It's kind of remarkable footage. So that particular cell, again, this is about an hour earlier than the Seminole tornado we just saw, but very similar situation. The environment is very favorable. You have this sort of embedded supercell within a line, and you certainly, right off the bat, you certainly have a very interesting reflectivity notch on the front side of it. From the lightning perspective, you've got marginal, fairly uninteresting lightning trends right now. You've got some lightning, but it's really not particularly electrically active here at 124Z. So let's step forward. There's a modest increase in total lightning, but as we move forward a little bit at a time, now we've gotten to 128. It's an increase, but there it is. At 129Z, there's a significant uptick. Again, going back to this concept of you have this marked increase in the updraft strength to indicate that this is going to become, this is becoming severe. So right around that same time, now you're starting to see the enhancement on the front flank, and I believe it's right around this time you start to have you have a wind surge interacting, and that produces you have the surge that interacts with the outflow boundary, and you get it appears that the outflow boundary helped instigate tornado genesis just southwest of Norman. So you have what is a fairly unremarkable looking storm from the lightning perspective. It was obviously interesting beforehand, but then you have this significant uptick in lightning here at 129Z, and then you start to see a more interesting reflectivity structure, and you see a corresponding increase in the velocity. This particular cell ended up producing, there was there was a brief report of some wind damage to the west of Norman with the cell right at 130 UTC, but this storm actually produced the Norman area tornado. I believe it was about 15 minutes later. And then this particular cell was responsible for quite a bit of hail in Oklahoma City, additional wind damage to the northwest of Norman, and the folks in Norman who lived this event and experienced this event, please correct me if I'm wrong. But this particular event had a pretty good lead time in terms of the lightning jump here as well.
Okay. Comments, questions from the audience? Again, as a reminder, go ahead and submit for those virtually on Slido.
Yeah, Todd and I were just talking about this event just a bit ago. The real challenge was, this small circulation west of the casino. The casino got hit, and the governor was there watching the Beach Boys. So, obviously a very sensitive situation. If only the weather knew in advance that was happening. Yeah, but, so the only, the thing that cued us in was, the eastward extrusion of that reflectivity that turned into a bokeh in that velocity signature you see, which is right there. So, see right there, you start seeing it, but then the updraft, you start seeing the lightning there just afterwards.
Jim, did you have another question, or were you just offering? Sorry,
Sorry, that was just offering additional.
Okay, I appreciate it. Now that's.
He was enhancing your presentation.
Yeah. Now the difficulty with not having any of these events to feature in Huntsville was I was relying solely on what I could get from the Norman webpage and the LSR. So thank you for enhancing that. I appreciate it.
Okay, anybody else before we move on?
Okay, so we've sort of addressed the main severe weather impact. For the last two cases, I want you to put yourself sort of in the mind of someone who maybe is providing decision support at the Norman office. This is on a Saturday night. Maybe you've got someone off to the side doing severe weather, but you're getting questions about outdoor activities. It's a Saturday night in October. Here's a line of storms. When can we get back on with our outdoor event? Maybe the storms have already gone through. Maybe you're up near Enid or Stillwater, and you're saying, well, when can we get back up to speed? When can we get things going again? So if you're just looking, and I think, personally, I think this is really where GLM is going to shine. So I'll focus a little bit more on the event density grid because it gives you a better spatial sense of the event, of the lightning. If you're looking just at the event density here at 240/60, okay, the lightning is fairly well confined to the. This is the event, yeah. So it's fairly well confined to the line, so you might easily be lulled into this false sense of security that, all right, this isn't something that is necessarily very troubling. It's not something that the folks behind the line need to worry about. But if we step forward one more scan, suddenly we start seeing something very interesting. We see these elongated.
That wasn't a change in 1 minute.
That So we went from 246Z to 247Z. So you have suddenly these elongated stretches of events that are lining up from the city, west, northwest, Wichita Falls, northwest, and even up over the Stillwater and Enid areas.
The point lightning is NLDN too. I don't know if you mentioned.
No, thank you. So the point lightning is NLDN, and so lest you think that these might be some sort of false detections, you also have corresponding NLDN detections occurring with these as well. This is something that has been well documented, and we have seen for quite some time with the ground-based networks in Huntsville, but also they're seeing quite a bit now with the GLM, is the concept of trailing stratiform lightning. So in my understanding, in almost all these cases, you're having trailing stratiform lightning. So when you have some sort of an MCS, QLCS, the lightning is very rarely just confined to the convective line. You often have these trailing stratiform flash events so that the lightning threat does not end with the leading convective line. So think about, again, put yourself in the position of you're working at the Norman Forecast Office trying to provide support to these folks that have already had to probably delay their outdoor events for a good chunk of the evening, and you're now seeing these trailing stratiform flashes, and you're thinking, okay, you're going to have to keep it going a little bit further. How would you message that? How would you convey this kind of threat, not just at the time, but leading up to this kind of event? Something else I want to point out that's kind of interesting. Can you go back to the full panel display? So you've got some weak convection occurring ahead of the line. Not particularly remarkable. It's fairly small in scale. It's fairly weak looking. I think your peak reflectivity, you do have a couple of 50 dBs in pixels, but you're starting to see lightning occurring out ahead of the line as well. And there's a good possibility that these may be getting some contribution from the convective line there at times. Can you go forward again a little bit more? You start to see some upticks in lightning here. And from the GLM perspective, it's seeing all this kind of one large spatial extent. So not only are you having to communicate to your customers that there's a threat of lightning along the convective line, but you also have to consider the fact that there's lightning that's occurring with these weaker cells that are occurring ahead of the line as well. Again, going back to this concept of what are you conveying to your customers? What are you telling them in terms of the threats? And in all likelihood, there's a good chance that they may have to delay their event far longer than maybe they had anticipated.
And just so to be clear, NLDN cloud to grounds are on there because GLM cannot distinguish between in-cloud lightning and CGs. So you need, CGs are the things, that's the lightning that it's dangerous, right? So you need to plot those along with, GLM. So you can see that there are CGs associated with this lightning out of the line.
And that's a really good point. For as great as GLM is going to be, for a public safety perspective, we're going to have to continue to use some sort of ground-based network to validate what is going to ground versus just to kind of validate, I think, what we're expecting from a conceptual level.
You mentioned public safety aspects. I'm thinking also aviation.
Oh, you're not going to be allowed to fly anymore. Right? Because if you're supposed to avoid lightning, I mean you can clearly see, right?
Well, so there's an interesting point made.
High-speed trains are where it's at.
Well, there's an interesting discussion I had with Jeffrey about the fact that now that we may get the true spatial extent of lightning, if you are, in my office we do a lot of, we do airport weather warnings for thunderstorms for our main airports. But if you're in Florida, for example, the concentration of thunderstorms in that area is extremely high. If we are getting a better sense of the spatial extent of lightning, how does that increase the amount of time that some of these areas are seeing downtime? There's actually a paper just published in GOE.
Obviously, I'm kidding, but Jeffrey's on the phone, and I've had conversations with him about this. Just imagine the Orlando airport, and you're using GLM, and maybe GLM is what you would consider your threshold. There's going to be a lot of lightning around, within a 5-kilometer radius of that airport, a lot of time during the summer.
All right, so someone open the door on it. Oh, I hear Jeffrey in the real.
You want to comment on it?
Jeffrey's got John.
I was going to comment too that the more I work with the aviation community, the more I don't want to fly either. The main issue we've done when talking with Aviation Weather Center, things like that, comes into talk about the convective sigma, so the significant meteorological statements. And a lot of times, that effort is really trying to focus on where is the convection, where is it happening, and where is it going to be in the next hour or two. We've had the chance to work with some of the ground-based lightning mapping arrays and show, hey, wait a minute, we can actually see these large spatial intent flashes, just as what Brian is showing here, what we've been discussing. And so AWC's kind of talked about, could that potentially result in some revisions to how we want to do a convective sigma due to what we're seeing with the lightning data. And I think from what Brian and Chad and everyone are mentioning here, that from this kind of safety perspective, this kind of DSS or impact-based decision support, particularly for safety, aviation, things like that, there's a lot of interesting stuff we're going to be looking into, and how do we kind of reconcile our current modes of operation with the new data that we're seeing.
All right, so Patrick, comment here.
Sure. So from a CWSU perspective, we issue center weather advisories, which are basically like SIGMETs that he just mentioned, but on a smaller scale. And so the lightning data for us is huge. The addition of the mapper data, the GLM, is going to be just another piece of the puzzle that we can use to help put our warnings out. And I basically, whether it's a cloud to ground or inter-cloud strike, any lightning strike is bad when it comes to an airplane. At least in my mind in aviation, because the plane may be just above the clouds or just below them, or between the ground and the clouds. So the addition of this data is huge for us, because it's hard to get a lot of air truth, I call it, as opposed to ground truth, as to what's really going on out there. So the E&I does a really good job, and I use that a lot on a daily basis for our center weather advisories. And rest assured, the planes will still fly. Because sometimes they still fly right through the box where we have it, warning out. Yeah, don't worry. Yeah, they still fly. Then I get a severe turbulence report about 10 minutes later. But from inside the box. But yeah, it's huge. So from a DSS perspective, for us, it's just more information I can provide to the controllers and the area managers of each area at the center I work at, and say, hey, look, this storm's bringing a lot of lightning. I just want you guys to know that there's been a big uptick in the last few minutes, and I have the warning out, just to let you know. So if I can give them more data, the more I get, the more I can give them, and then they can make more decisions that way. So it really helps.
This is Jeffrey again. Oh, sorry.
Just provide a little more local Norman enhancement, I guess, to your presentation there, Brian. Jim mentioned the governor was attending the Beach Boys concert at the casino that was hit that night. But you also mentioned IDSS for outdoor activities, and I'm just curious, does anyone know what type of outdoor activities we have in Oklahoma on Saturday nights in October?
Baseball, football?
Yeah. Right. So, but we did luck out with this particular event. Neither OU or OSU have home games in the state this day. So that's one concern we would normally have. And
if you would have 120,000 plus or so outdoors attending college football games in the state. But I just wanted to address that University of Oklahoma has a very good, very active emergency management department led by Dr. Kevin Clay. So we would be providing him support, but they would actually be making those calls independently. But of course, we'd be supporting those decisions.
Yeah, thanks a lot, Todd. And actually, we didn't cover it with this event, but about a week later, so I'm a Penn State alum. About a week later, Penn State played Michigan State in Michigan on a late October afternoon, and they had elevated thunderstorms that moved right across the area where right across East Lansing, and they had to delay for I believe it was about 3.5 hours because of trailing stratiform lightning. They just couldn't shake it.
I'm just going to speak briefly about the aviation concerns for especially since the connected segment was mentioned. I know that some people in our office have actually started using this a little bit, mainly for connected initiation, because you can actually see the lightning before our scans come through, because it goes through more quickly. I do think something that somebody has actually, I don't know if anybody's actually done this yet, but it's considered low top convections. And we do have stuff that comes around the Great Lakes region that the tops are in their 20s, so aircraft can easily fly over, but it will have convection with it, which means we have to cover it. So it would be interesting to see what this does over the winter time when we have convection around the Great Lakes.
And that actually will go both ways. This particular event is almost ideal, but something we certainly deal with in not just the southeast, but in large swaths of the country is cool season, high shear, low cape convection. And we've had tornadoes in downtown Huntsville that occurred with zero lightning because the updraft does not get out of the mixed phase region, so it does not produce any lightning. We don't get the droplet collisions you need for lightning generation, but you still have severe weather ongoing at the ground level. So we can't just use lightning as a panacea. It's not going to fix everything. It's important to understand the underlying conditions that require it.
Okay, last question in the back. For those that are looking at the slide, I forgot about that. We'll try to take those in a minute.
Chad, could you, I know you're in the process of changing things up there, what I'd really like to be able to see is more than, it looks like you have maybe 5 frames up there. Would it be possible to go through more frames and loop that so we can see what's going on physically where during that 1 minute where we get the increase in the trailing stratiform regions? Just curious what's going on physically there. But then I've made the change.
Well, let's look at this one and then I can easily have more. Alright, so we're not too far behind. Alright, we're gonna jump up.
Okay, so the kind of the last piece of the IDSS lightning safety puzzle, where we are right now and into western Missouri, northern Missouri was also included in a slight risk on this particular day. I'm not going to address the severe weather component, but you did have thunderstorms stretching well to the north of the Oklahoma City area we were talking about earlier. So again, the same concerns apply here. And so we're still looking at on the bottom left. We're looking at event density with the pluses and minuses indicating NLDM lightning, and then the group density on the bottom right. You have a sort of an MCS kind of look, a QLCS, a broken line extending well up into northern Missouri here. You step forward from 220 UTC to 221 UTC. You have what I honestly, the first time we looked through these data, I thought it was an error. I thought it was a mistake. You have almost such an incredible burst of trailing stratiform lightning that I thought it was a mistake. But there are a couple of different things that could be going on here. One is this could conceivably be only one or two flashes that have triggered a great deal of events. You see a couple of positive CG flashes, and caveat, I am not an atmospheric electrification expert. I just play one on TV. And so this particular area, you get a pretty good response in the radiance. So the positive flashes tend to be brighter than it is on your sailing. So you may be getting a lot of response here from the optical sensor, and that happens to correspond very well to the positive flashes. But there's just incredible, this is real. And you see, when you step forward another scan, you see the corresponding response in the MLDN data. Again, a lot of positive flashes in all of this. Now, why is there a difference in time? That's a fairly minor file difference, definition of how they adjust where, or how they define what piece of the file is occurring from which time to which time. It's something that can be very easily corrected and will be when it's out of operations. But you have this incredible looking, what I thought was a mistake when we looked at it, but it's a real occurrence, and it's a real significant issue for exactly decision support.
Scott, do you want to add anything about the positive flashes, or just
Well, just in general, I guess in the stratiform region you have less cloud above it too, so it would get brighter. The idea that you're showing here, I think, is really important in how quickly it can change like this, and you can have these extensive flashes. And so when you're looking at the event data like this, what you're seeing, each event is a 2 millisecond period. And so if this is 1 minute worth of data, where you see the white, a lot of those 2 millisecond periods are filled up with lightning, if that makes sense. So that's why with the event data you see such a drastic increase over such a short period of time.
All right, we have time just for a couple more questions. Let's address one thing real quick that you probably all have been staring at, and it's also listed up there in the slide down, and that's the checking what dark stripes you're noticing through the so Scott.
Yeah, I could add to that. So there's two sources of it. One of it is how AWIPS grids. The HWT, Kristen Calhoun and her group did a great job during the spring experiment looking at it this year. And what they found is if you used an 8 by 8 kilometer grid, you would end up with those stripes. If you used a 10 by 10 kilometer grid, then you would get double, triple, quadruple counting. And so that's part of the reason why we're taking a different route with Brian Gockel and his team to get the data in here, is to try to alleviate some of these issues. The other big thing, many of you may have heard of what became affectionately known as the Charlie Brown stripes. That's something that's been fixed, and it actually had a much bigger impact than we knew going in. And so what it ended up being was you were having, it was a rounding issue. So there was a rounding issue in the ground system. So this is one of those things they fixed, and they fixed this rounding issue, and all of a sudden it got rid of the Charlie Brown stripes. And so any data after Halloween, you will no longer see those Charlie Brown stripes. So all of that would be AWIPS. And it just goes to show we're still fixing, we're still fine-tuning the ground system to make sure that it's doing what it's supposed to be doing. So yeah, that's what's contributing there. That's what's showing those stripes. That won't be shown once the data is operational.
So let's take one more question from slide out. That second one from the top. Can you define the term lightning jump as it will apply to GLM? Are there any planned AWIPS algorithms to help alert forecasters to GLM lightning jumps? Obviously here, Brian was qualitatively suggesting that a lightning jump is occurring. The lightning jump is statistically determined, and it's very difficult for meteorologists, forecasters on the fly to do that. So Brian, would you mind commenting?
So yeah, I can speak a little bit to sort of the operational impacts. And so there's research from Chris Schultz at the University of Alabama in Huntsville as far as what constitutes a lightning jump. And his research has been mostly that you're looking for 2 times the standard deviation of a 10-minute running average for a storm. And the problem there is when I'm in operations, I can't calculate that mentally. Obviously, that's a huge problem. So in our operations, we've been sort of maybe trying to look out for, trying to do the math roughly. I mean, I can't calculate that very well, but I can try and get a feel for, some of what you saw here, where we went from, 34 to 61 to 128. That, in my mind, is more than sufficient. So, everything that we've done at the local level has been sort of ad hoc. I'll have 2 more things. There is a tool in AWIPS called the Tracking Videogram tool. It requires forecaster interaction. You have to put you get this little dot on the screen with a radius, and you can put the dot over your storm and track it. You have to track it manually, and it will give you sort of a line graph time series of whatever you're trying to measure. So that might give you a little bit better qualitative sense. It still won't necessarily trip a lightning jump formally. It won't say, hey, this is something you need to pay attention to. But there's been several different efforts between the Weather Service and other groups to try and automate the lightning jump side of things. And I think that's certainly only going to increase and improve as we have more access to GLM. Weather Service will.
And Chad and Brian, I can tack on a little bit as well that there is going to be effort to continue with GLM since the algorithm is going to be a little bit different from working with the ground-based lightning mapping arrays. There's also the interest of trying to incorporate the new data that GLM provides, which is the optical data, and then also I know Scott has been trying to discuss some other things too in terms of going forward with automated activities.
Okay, thanks, Chad. I guess at this point, let's give Brian a round of applause.